So we would end up here with 0.3 t to the negative 1/2. Well, it might not have seemed like the logarithm was making things simpler, but we did get quite a simple answer here at the end.
And this already took care of doing the derivative over the original, right?
That's right. So we don't need, so we're not using this method.
Right.
This is the alternative to that method.
Okay.
If we tried to do this now on top of that, that would be double counting. So that would mess us up. So let's go ahead and finish off the problem. We've discovered here that here's our derivative, and we should be able to answer the question. Let's finish this and give an actual answer.
T equals 5 years, so 0.3 times 5 to the negative 1/2.
Yeah. Might as well get a number here. You have a calculator with you?
Yeah.
You don't get to use a calculator on your test, do you?
No.
All right, well, let's use it here anyway to get a number. What did you get?
0.134.
Okay, so approximating, we get 0.134. So it looks like you saw that you have to put this exponent in parentheses on your calculator to let it know that it's all one exponent. So what's the answer to the problem?
Move it over times 100, so 13.4%.
They were basically asking us for the percentage growth rate. So the answer is 13.4%. So this formula gives us the percentage change expressed as a decimal. And then we have to remember to turn it into a percent.
In the first one, would we have to times by 100 also?
That's right. So this formula also gives you the percentage change expressed as a decimal.
Okay.
And then if you wanted to put it into percent terms, you'd have to multiply that by 100 as well.
Okay, that makes sense.
So this tells us that in 1 year, the value of the investment will be approximately 13.4% bigger. Now the nice thing about having this formula is now we can quickly use it to find the percentage growth rate in any year.
Oh, you just plug in however.
We can just plug in any time
Okay.
that we want to. Well, this problem gave us more trouble than the earlier one, so let's review what the steps were. So now we've learned two different ways to figure out percentage changes. You can figure out the derivative and divide by f, or you can take the logarithm and take its derivative. And which way should you use? Well, whichever one looks like it's going to be simpler, although it seems like sometimes the instructor might give you a hint as to which one to use. So then you just do what the instructor wants. The more you practice, the better your judgment will get for when the logarithm will simplify things. So here we should say, gee, when we take the log of a product, that will separate this into two pieces, and this is not, the derivative of this will be 0. And plus, the log of e simplifies very nicely. So if you're comfortable with logs, you can see that taking the log here will simplify things a lot, whereas taking the log would not have simplified the previous problem that we did very much. But you can see that one of the biggest things that gave us difficulty here was not the calculus, but the algebra, which is, I find, one of the main difficulties people have in calculus. One of the biggest problems here was just the algebra of logs. So we just need to review here's some things that you need to know about logs. By the way, while we're at it, is this true?
No.
No, that would be a trap. This is true, not this. So you definitely want to watch out for this. This is the reason why it was not helpful to take the log in the previous problem, because that was a sum, and the log of a sum doesn't simplify. Logs simplify products, and they simplify powers. They don't simplify sums. Well, the previous problem had a lot of sums, whereas this has products and exponents. You were going to say?
I was going to say also quotient, right?
Yeah, that's right. So yeah, quotients are similar to products, that's right. So the log of a product is the sum, and as perhaps you're remembering, the log of a quotient is the difference between the two things. And remember, this idea does not apply to exponentiation. You can't just take the exponent off of an exponential function like we had here. What else did we use? Oh, the other thing we saw is the derivative of a log is the reciprocal, but that's only when you're taking the log of a variable. If you're taking the log of a constant, its derivative is just 0. That was the reason why this simplified our life.
Also within this section from the homework exercises, we had a few questions.
Okay, did you want to move to that?
Should we go over elasticity of demand?
Yeah.
Yeah.
Okay. So we're looking at the elasticity. All right. So now we're going to think of f as a demand function. So maybe I'll put in a d here instead of an f. Now the demand depends on the price. The higher the price of the good, the less consumers are going to demand of that. So you simply, what's the meaning of the derivative of this function? Well, I just said that when the price goes up, people will demand less, and this tells you approximately how much less. So for example, this would tell us that if you increase the price by $1, people will demand approximately 5 units less. If the derivative was 5, then every time you increase the price by $1, consumers will demand approximately 5 units less. But again, maybe what we really want to know is the percentage change in the demand.
So this is also percentages?
This is also about percentage change. That's how it's similar. However, there is a difference here as well.
You multiply by a negative.
Let's take it step by step. So, what we were talking about before is we were talking about the percentage change in the y variable when you change the x variable by 1 unit. So we were focusing, for example, we might talk about the percentage change in population when 1 year passes.
Okay.
One thing to notice there then is we were focusing on the percentage change for the dependent variable, but we were not focusing on the percentage change for the independent variable. Well, elasticity is when you focus on the percentage change of both the dependent and the independent variable.
Okay.
So now we're going to be talking about what's the percentage change in the demand when you increase the price by a certain percent. That's what elasticity is about. It's the percentage change.
So it reflects both the x and the y.
That's right. Well, it reflects that we're focusing on percentage changes in both x and y. That's right. The previous concepts we were looking at also reflected x and y, but for the previous concepts we were focusing on the percentage change in y and just the unit change in x.
Okay.
Now we're going to focus on the percentage change in both of them. So the elasticity of demand is the percentage change in the demand divided by the percentage change in the price.
Okay.
Whereas before we would just have been focusing on the change in the independent variable. And it turns out that the way to calculate that is here's our basic formula. We'll have to make one modification to this, but here's our basic modification, our formula for finding elasticities. Notice this is very similar to the previous formulas. The thing that's different is we're also including the independent variable in the numerator.
Okay.
If we were leaving this independent variable out, then this would just be the percentage change in demand when you increase the price by 1 unit. But now that we're putting P in here, this is going to tell us the percentage change in demand compared to the percentage change in the price. Now, one complication from this is when you increase the price, does the demand go up or down?
Down.
It goes down. So there's a negative relationship between these. That is, this derivative is negative. But people get tired of talking about negative numbers all the times. So in the book, they multiply this by a negative sign so the elasticity will come out positive.
Okay.
So the derivative here is negative, but it's tedious to talk about negative numbers all the time, so we're going to just drop that negative sign from the derivative. Mathematically, that means we're multiplying by -1.
Okay.